Okay, so let's continue our exploration of piecewise functions. The next problem in your notes paper is just evaluating a piecewise function. You don't have a graph at all, so we're simply using the equation. So if we want to find g of negative 4, again, you're focused on getting only one output for every input because, again, it is a function. So negative 4, I need to figure out which domain does this fall in. And I know that negative 4 is less than or equal to negative 3, which means I'm going to be using this top function. And in this case, the function is 7. That means no matter what I plug in that's less than or equal to negative 3, I get an output of 7. So g of negative 4 is 7. G of negative 3. Even though I see negative 3 show up in multiple places in the actual function, I know that when it actually equals negative 3, that corresponds to this top function or this top piece. So again, my output would be 7. For g of 0, 0 is going to show up in multiple places again, but it's only equal to 0 in the second equation. So that means I'm going to plug in 0 for x here in the second piece. So 3 times 0 plus 2. We know that 3 times 0 is 0, plus 2 equals 2. So g of 0 equals 2. And last, g of 2. 2 is greater than 0, so I know I'm using this bottom function, or this bottom piece. So negative 2/3 times 2, I multiply across, and I know that that's negative 4/3. The next thing that I want to talk about is actually graphing the piecewise function. And I would say that this is probably the most challenging. My advice would be to think about ahead of time what this is going to look like. So I have two pieces, so I know I'm expecting two different pieces. Both are lines, both have positive slopes. And then I can see that negative 2 for my x value is kind of the cutoff. So if I'm thinking about it, let's see, here's where x equals negative 2. If I want to, I can kind of picture it just by maybe just visualizing a little vertical line there or actually drawing it in. It's up to you. You don't need to draw it in, but I should have one piece over here where x is less than negative 2 and another piece over here where x is greater than negative 2. And the piece that's over here where it's greater than negative 2 is also going to have a closed circle on that x equals negative 2 because of this x greater than or equal to negative 2. So I'm going to have two rays, basically, going in opposite directions. Let's focus on this one first. The 2x plus 4, this is where x is greater than or equal to negative 2. So I'm expecting this to show up over here in this part of the graph. Now, we're pretty comfortable with graphing 2x plus 4, right? We know that the y-intercept is going to be 4. So 1, 2, 3, 4. I can go ahead and plot that point. And then I know the slope is 2. So up 2 over 1, up 2 over 1. I can go to the left. And I know that I'm going to have to stop here, right where x equals negative 2. And the fact that negative 2 is within the domain, I'm going to make that a closed circle. So there's a closed circle there, and then I'm going to continue drawing my ray that direction. The next piece is usually what's a little bit more challenging, simply because I can't really start this here at the y-intercept because technically this domain doesn't allow that piece to go that far over. So here's kind of my advice. I usually take the function, so in this case the 1/2 x minus 3, I'm going to work with it over here kind of off to the side. What if I were to make a table of values? I know that negative 2 is the cutoff, and I know it's going to be an open circle. So if I were to plug in negative 2, I need to think about what would I get out, and then I need to remember that when I graph it, I'm going to make this an open circle. So if I were to plug in negative 2, half of negative 2 is negative 1, minus 3 more is negative 4. So at negative 2, negative 4, I could have an open circle. This domain says that I can plug in any number smaller than negative 2. So it's up to you. You can either think about the fact that a slope of 1/2 is going to be going like this, up 1, right 2. So to go backwards, I could go left 2 and down 1. I could continue it that way. Or maybe I could pick another value that I'd want to actually plug in. So maybe I want to plug in negative 8, for instance. Well, half of negative 8 is negative 4, minus 3 is going to be negative 7. I could go here and I could actually plot that point, negative 8. 1, 2, 3, 4, 5, 6, 7, I can see that it's going to follow that slope of 1/2. But once I'm done here, you can tell that I do have a piecewise function. Still is a function, it passes that vertical line test. Um, and it looks reasonable. I can go through, I can double check the slopes, I can double check that if I were to continue this, it does in fact intersect at -3 there, which is what we were expecting. So then the next thing that you might want to do is actually go through and evaluate. Again, you could use the graph if you have it, or you could use the equation. So f of -2, I can look at my graph. I'm looking for the closed circle. My output would be 0. F of 0, I can see in my graph that my output would be 4. F of 7, well, that's going to be over here. I don't see that in my graph, so I'm going to go ahead and plug it in. 7 works in the top domain. 7 is greater than or equal to -2. So I would use that top function, or that top piece. 2 times 7 plus 4. 2 times 7 is 14, plus 4, we get 18. And then f of -12. -12 works in the bottom domain. -12 is less than -2. So I could take half of -12, and then I would subtract 3. Half of -12 is -6, minus 3 more, we get -9. Go ahead, try this next one on your own, see how you do. I'm still going to explain the whole thing, but maybe pause the video and give it a shot just to see how you do. But if I were going to go ahead and graph this, I'm going to show you, just some pointers. It's up to you. You could graph every single part completely and then use your eraser to take into account the domain. It's really your call. But here's one way that you could go about it. So if I'm going to focus on this top part, I'll do the top one in green. X squared minus 5, I know that this is going to be a quadratic. It's going to look like a parabola. And it's only going to show up from -1 right here, where x is -1, to the left. So I'm expecting this graph just to show up right here. So let's work with it. I'm going to work with x squared minus 5. I'm going to make a table of values for this. And every time that I make my table of values, I include any number that's written in the domain over here. And then based on whether or not it has the or equal to part, then I'll decide if I actually, want to close the circle or open it. So I'm going to go ahead and plug in -1. -1 squared is 1 minus 5 is -4. Because -1 is within the domain, I'm going to go ahead and I'm going to close this when I graph it. It's going to be a closed circle. So at -1, -1, 2, 3, 4, let's close that. And then I know my domain is x is less than -1. So I can plug in numbers that are smaller than -1, like for instance, -2. -2 squared is 4 minus 5, -1. So at -2, -1, I'd have another point. Let's continue this. I could plug in -3. -3 squared is 9 minus 5 is 4. So at -3, 1, 2, 3, 4, I'd have another point. So I can see that this is following along. It's going out to the left here, but it's stopped at -1. And I'm sure that yours will look much nicer than mine, but it's a parabola. It should have a slight a curve to it. Let's do the next one in blue. This one goes from -1 to 3. So I should see it from -1 to where x is 3. This graph should show up in this section. Okay? So if I'm looking at 2x plus 1, again, it's up to you if you feel like you need to do this. But you could make a table of values, and I always plug in the numbers that show up as part of the domain. So I'm going to plug in a -1. I'm going to plug in a 3. But when I plug in -1, I have to keep in mind that's not actually part of the domain. So this is going to be an open circle. But 3 is part of the domain, so I can actually close this one when I graph it. When I plug in -1, 2 times -1 is -2, plus 1 is -1. So at -1, -1, we have an open circle. And then when I plug in 3, 2 times 3 is 6, plus 1 is 7. So at 3, 1, 2, 3, 7, 1, 2, 3, 4, 5, 6, 7, we have a closed circle. And hopefully this follows along with the fact that our slope is 2. Up 2 over 1, up 2 over 1, we can see that it looks like this is going to work out. And we would connect those. Every point between those counts. Every x value in between -1 and 3 is part of the domain. And let's do the last one. The last one's interesting because the function is just negative 6. So I know it's going to be a horizontal line, and it's only going to happen where x is greater than 3. So starting at 3 here, it's going to show up from 3 and over to the right. Well, I can't technically plug in 3, but I know that if I were to plug in 3, I would get out negative 6. It's just going to be an open circle. So at 1, 2, 3, negative 1, 2, 3, 4, 5, 6, we would have an open circle there. And then for every other x that is larger than that, you get an output of negative 6. So it's going to be that horizontal line there. I'm finished. That's what it should look like. And I can see that a vertical line is going to only hit the graph at one point no matter where you put it. So this is truly a piecewise function. Last but not least, you need to evaluate the function at f of 3. When I look at 3, I should get out 7. F of negative 1, you should get out negative 4 because you're looking for the closed circle, not the open one. At f of negative 4, you could look on the graph. Ooh, I don't think it's going to actually show up here, so I probably need to plug it into the function. Negative 4 is less than negative 1, so I'm going to plug it into that top function. Plus, I knew that it would be a continuation of this green part, which corresponds to the top. So we would plug in negative 4. Squared is 16 minus 5. We would get 11. And finally, f of 9, we know that's over here. We're going to get out negative 6.